Welcome to GPR Method and Theory for Concrete Inspection, brought to you by GSSI Academy. In this training, we will cover the following. What is GPR? What are some of the applications it's used for? We will break down the components of a GPR system, talk a little bit about the history of GPR. We'll also look at how to interpret the data, as well as some of the advantages and limitations of using it as a survey tool. Starting in 1887, Heinrich Hertz notes that radio waves are reflected by some materials and can go through others. In the 1920s, radar is researched by the military. Scientists note that the speed or velocity of electromagnetic energy through air can be measured. In the 1940s, while testing the first atomic bomb, scientists concluded that electromagnetic energy can penetrate deep underground. Scientists note that the time and signal strength vary with distance and material type. In 1970, GSSI builds its first commercial GPR unit, starting as a service provider and then moving into manufacturing soon after. After decades of leading the world in GPR, GSSI celebrates 50 years of innovation in 2020. Ground-penetrating radar, commonly referred to as GPR, uses radar pulses to image the subsurface. This non-destructive method uses electromagnetic waves to detect the reflected signals from subsurface structures. With GPR, we are transmitting and receiving high-frequency electromagnetic waves. We transmit a wave into the concrete, soil, or subsurface, and it reflects off different materials it interacts with. Once the information is received, we will know a little bit more about what we just traveled through and what type of materials might exist below. At 2.7 gigahertz, we're at an appropriate frequency for concrete inspection. It's important to note that GPR is very safe to be around, with very low power emission rates, less than 1% of the signal strength of your cell phone. We're transmitting an ultra-wide band of energy, or wide band of frequencies. Think of it as a bell curve. In this case, we're not only transmitting at the 2.7 gigahertz frequency, but it also has an upper and a lower limit. In terms of frequency, we're talking about the measure of cycles per second. 1 cycle per second is 1 hertz. In this presentation, you'll hear me talk about megahertz and gigahertz. This refers to millions or billions of cycles per second. Let's look at an array of different antenna systems and see how they vary in frequency. Looking at high-frequency systems that get us very high resolution, all the way down to lower frequency systems that get us much deeper depth penetration. Starting with the Structure Scan XT system at 2.7 gigahertz, we get very high resolution data, with the trade-off being we only get about 24 inches in depth penetration. Now let's look at a lower frequency system and break it down to its elements. With this Utility Scan Pro system, we have a SIR 4000 control unit operating as the brains of the operation, as well as a 400 megahertz antenna, getting us about 8 feet underground in this case. We also have a survey wheel encoder tracking our distance, as well as a survey cart that allows us to keep nice straight lines and track our data in the field. To the right, we have a data set indicating the interface between different soil layers, as well as a hyperbola that could represent a utility pipe. Looking at the 270 megahertz system, we get about 12 feet underground, but as you can see, the image is just not as distinct as the higher frequency systems. Going lower in frequency to a 200 megahertz system, we get about 25 feet underground. In this case, we're likely looking for large storage tanks, shallow geological features, bedrock, water tables, etc. Using the 100 megahertz, we can go about 100 feet deep in certain soils. This antenna actually uses 2 large orange boxes being pulled behind here. Because the antennas are so big, we need to put them into separate boxes. One acts as a transmitter, one acts as a receiver. Lastly, we have the MLF antenna for multiple low frequency. Using 16 to 80 megahertz, this antenna gets us about 1,000 feet underground using 2 poles that we can add or remove extensions to. They will transmit and receive different frequencies depending on their distance. GPR transmits in a very specific range, the ultra-wide band of energy. Because we're not the only sources of EM sharing this real estate, we have to prove to the FCC that we're not interfering with other transmissions in that range, such as radio and cell phones. So much like submitting a new drug to the FDA, we have to submit all of our antennas to the FCC to prove that they're weak enough as to not interfere with those sources of electromagnetic energy. Because our antennas are weak enough to not interfere with those sources, we tend to accept interference from those transmissions. This is an example of some typical interference as it shows up on the screen. You will see this type of interference at the bottom of the signal where it's at its weakest. Also note, there is no interference from Wi-Fi, Bluetooth, or any other sources of energy that you may encounter in an office scenario. This interference, of course, can be easily avoided by placing your phone in airplane mode. To combat this interference, we heavily shield our antennas, surrounded by metal and insulated with a carbon-laden foam. This allows the signal to transmit straight into the ground and not all around as the signal naturally wants to spread all over. This shielding focuses the signal where it wants to go, straight down. You may notice these two green bow tie shapes acting as the transmitting and receiving elements. We transmit high frequency waves into the ground and get a reflection from the receiver. Let's imagine what this might look like. The transmitter emits a wave of energy at about 4,000 pulses per second. This wave reaches the target and is reflected back to us as a high frequency electromagnetic reflection. What we measure here is what we call the time of flight, or the two-way travel time. The time it takes for that energy to travel through the concrete and reflect back, making that round trip back to the receiver. What we're able to view in the data as we cross over a linear target in a perpendicular fashion, at 90 degrees, we produce this upside-down V shape, which we refer to as a hyperbola. The time of flight going down the leading edge and the trailing edge is long relative to going straight over the top. Now that we've received the data, we need to interpret it on the screen. We can understand patterns visually through the use of shaded hyperbolas more clearly than a bunch of wiggly lines on the screen. To make our lives easier, we assign color tables. By adding color and pixels, the image is easier to interpret. Important to note here, positive amplitude or signal strength is labeled as white, whereas a negative amplitude is labeled as black. Notice our oscilloscope in relation to positive versus negative, black versus white. The pulse will go to the right if the target is labeled positive, whereas it will go to the left if it is labeled negative. This is what will allow us to identify things like depth or material type. The system initially understands the data as a series of these scans all stacked together. If we were to isolate one of those single scans and break it down to either positive or negative, we'll note that anything to the right is going to be labeled positive with a white color. Anything to the left will be labeled negative with a black color. This will help us identify not only depth, but material type. For instance, whether the target is metal, positive, or air-filled PVC, which will be labeled as black or negative. Let's look at some GPR data and break it down to its elements. First, try to imagine a piece of rebar sticking straight out of your screen at 90 degrees in a cross-section. What you see horizontally is distance, tracked by the survey wheel. What you're seeing vertically is the two-way travel time, measured in nanoseconds. The system initially only understands two things, distance and time. But we want to know depth. Depth is calculated once we know the time it takes for the two-way travel time based on the properties of the subsurface. Time to depth is an approximation with a 10% margin of error. This will improve with more experience. It's also important to note that radar cannot calculate the size of the object in terms of diameter. Let's look at these hyperbola shapes. It's important to note that we're seeing white as a positive amplitude reflection and black as a negative. In order to understand where the top of the object is, we must look at the first strongest color, which in this case is white. Also note that our oscilloscope is showing a positive pulse to the right. We see that positive correlates with white and negative correlates with black. Next, let's talk about the dielectric constant. Dielectric is a unitless measure. It's a measurement of speed. Energy moves fastest through air and slowest through water. Every material under the sun has a dielectric between 1 and 81. Instead of saying GPR travels at 186,000 miles per second, the speed of light, we assign a value that's a little easier to digest. We say that it has a dielectric of 1. For all intents and purposes, air is a vacuum, so as a ratio, it's 1 to 1. Water is 81, as radar travels 9 times slower through water, so the ratio is 1 to 9. Every material under the sun has a dielectric between 1 and 81. Radar travels fastest through air and slowest through water. The more moisture in a material, the higher the dielectric. As long as depth is a concern to us, dielectric is very important. The more accurate our dielectric, the more accurate our depth. If dielectric is so critical in terms of calibrating our depth, then how do we figure out the dielectric? Well, the first method is what we call published reference. This is all based on the age of the concrete. Let's say we have 3 concrete types: dry concrete, medium, and wet. The dry concrete could be several years old and fully cured. We would set the dielectric anywhere from 4 to 6 in this case. Let's say the concrete was poured within the last month. It's not fully cured, and it's still drying out. We would set the dielectric to anywhere from 7 to 9. What if the concrete has been freshly poured and is still curing? In this case, we would set the dielectric anywhere from 10 to 15. The next method for calibrating the dielectric is what we call migration, or hyperbola fitting. This is based on the theory that if we have dry concrete with a low dielectric, the energy moves very quickly. This will produce a much wider hyperbola. With wet concrete or green concrete with a high dielectric and a low velocity, the GPR will produce a more narrow hyperbola. Based on this theory, we can analyze the width of the hyperbolas to figure out our dielectric. To do so, we simply collect some data, produce crosshairs on the top of our hyperbola with the backup cursor and horizontal cursor. Under calibrate, we will produce this blue hyperbola on our screen. From there, we simply adjust the width of the blue hyperbola to match the contours of our data, and by doing so, we've just calibrated our system to that particular slab. Not all slabs are created equal, so every time we go to a new slab to collect data, we want to run through this process, ensuring that our depth calibration is as accurate as we can make it. The last method, and the most accurate way to determine the dielectric, is what we call ground truth. As concrete is homogeneous, it makes it much easier to use this process. To ground truth properly, we want to be able to physically measure the depth of a target. Let's say we have rebar that we're able to physically measure with a tape measure. Let's also say that the rebar is measured at 5 inches deep. We just crossed over that rebar with our structure scan system, and the system's telling us that it's 6 inches. We simply go into set depth, change the value to the correct measurement that we just measured. In doing so, we've just calibrated our system to that slab using a known depth. Determining material type. Let's say we have some average concrete with a dielectric of 10. We encounter a metal target which has an infinite dielectric. We're going from 10 to infinity, which is a low to a high change, which is positive. In this case, the first strongest color is going to be white for metal. Metal is a perfect reflector for GPR. The radar energy is going to bounce right off of metal like a mirror and will not penetrate through it. In the case of metal, the first strongest color is going to be white. We'll see a black, white, black pattern on our display. Note that the oscilloscope goes to the right, which we know is positive. Let's say we have an air-filled PVC. Dielectric of air, as we know, is 1. If we're going from 10 to 1, now we're going from a high number to a low number, which is a negative change. The first strongest color in this case is going to be black, with a white, black, white pattern. Looking at our oscilloscope, everything checks out as the oscilloscope goes to the left, indicating a negative amplitude. Lastly, let's look at a PVC pipe with water in it. Again, we're going from a low number to a high number, 10 to 81, which is a positive change, much like metal. So the first strongest color, again, is white, displaying a black, white, black pattern. The difference, however, is in the faintness of the target. The larger the dielectric change, the stronger the reflection and the brighter the target. The smaller the dielectric change, the weaker the reflection or the dimmer the target. Let's try to break down another data set. To the untrained eye, we might assume that there's 2 rows of rebar or reinforcement in this data. What we're actually seeing is the tails of these top rebar that are long enough to, in fact, obscure what you would normally see as the bottom of the slab. By migrating those tails into dots using focus mode, we can now reveal otherwise obscured targets, like in this case, the bottom of the slab. Since so much of our signal is absorbed, we use a method called gain to counteract that absorption visually, sort of adding some screen contrast to our data set. This isn't changing the signal in any way. However, by using auto gain, we're essentially turning up the volume of the signal to get a better view of our data, adding screen contrast. For a little bit more control over your gain curve, you can use a feature called manual gain. Let's start with a weak signal like this. Notice how our data is very dim and hard to see. By adding some gain, we've increased those amplitudes, visually adding contrast, and allowing for an easier to interpret visualization of our data. If we add too much gain, however, the signal is now clipping. Information is now truncated and we're losing some of those details. We're actually clipping the data from the record. As a result, we get super high contrast data that's more difficult to interpret. Let's talk about noise. We can easily break this down into 2 categories: high frequency noise versus low frequency noise. High frequency noise is caused by adding too much gain to an already weak signal. What we get is this snowy staticky effect, as well as a craggy looking oscilloscope. With low frequency noise, we may encounter a subsurface material that's overly saturated, causing this banding effect all the way down our signal from the data. By using background removal, or the band filter, we're taking each individual scan and anything that repeats horizontally is removed, thus getting rid of this horizontal banding that's otherwise obscuring our targets. Next, let's look at scan density. With scan density, we have 2 options, normal or high scan density. By increasing our scan density, we're stretching our data coast to coast. In the event that we have a particularly small object that we're trying to locate or bisect with our backup cursor and finding difficulty, we can increase our scan density to stretch that data left to right. 2D versus 3D. 2D data collection is simply scanning and marking the surface based on interpretations on your screen. It's quick and allows a map on the surface indicating the direction and orientation of any subsurface targets. If more information is required, 3D can help map and archive and indicate anything dangerous in the slab. 3D data collection is used if you need a little bit more confidence or a better level of interpretation of the subsurface targets. By creating a 3D image, we're then able to slice down through those targets to reveal different layers, creating a visual map and peeling back those layers to reveal different levels and different targets. Applications for concrete inspection include rebar, post-tension, wire mesh, and void detection. Utility inspection, or the utility scan systems, can be used for locating utility lines, underground storage tanks, steel reinforcement, and voids. The road scan system is designed to measure pavement thickness, using up to 4 separate 2 GHz antennas that can be mounted using a SIR-30 control unit, which connects to a dashboard computer. Real-time data collection can be captured at highway speeds. With the bridge scan system, we're using a high-frequency antenna with a three-wheel cart, making parallel passes over the top, looking for the strength of reflection over rebar. We can then assemble a 3D grid, pick all the rebar, and create a plot based on amplitude and can determine rebar deterioration based on water absorption. GPR is also widely used for archaeology. Based on what the surveyors knew about the site, they were able to determine the location of these unmarked graves using radar. GPR is also used in forensics. What we have here is the victim on the right and the data on the left. What we're seeing in the data is what we refer to as an anomaly. When the forensics team was scanning along, they noticed one particular area that looked different or anomalous. As it turns out, this is where the soil had been disrupted, indicating an anomaly on the screen. Using a big 100 megahertz antenna, geophysicists use this very low frequency antenna to see bedrock and volcanic ash deposited by windstorms in Antarctica. Notice the depth scale, 300 meters. Mining is also an application for GPR because it's so easy to find metal underground, because metal has such a high amplitude value that it's often easy to find with GPR. No matter what type of metal, GPR displays any metallic object with a positive amplitude. This survey uses the SIR-2, which is the great-grandfather of the SIR-4000. One of our more unique systems, the Life Locator, is used for search and rescue. These systems use a wireless transmitter that allows search and rescue teams to locate people that are still breathing and potentially rescue them. The sensitivity of these antennas is so great that it will actually pick up chest compression and decompression of a victim that's buried and needs rescue. The slightest movement of the arm can be detected by these systems to help triangulate the position of someone that needs rescue. Radan 7 is GSSI's post-processing software. With a familiar Windows-based interface, it's easy to run various processes to enhance your data set. You collect the best data you can in the field and then bring all that data into Radan to process it, sort of like Photoshop for GPR data. Let's review when not to use GPR. We know that GPR cannot penetrate metal and in fact acts like a mirror. So any type of pandecking or corrugated metal in your slab will block that radar and not allow you to see anything beneath it. We cannot size rebar in a practical sense. Very young concrete, less than 1 month poured, the conductivity is too high. Small cracks, not enough difference for GPR. An extremely small area. It is recommended that you collect as much information as possible to make the most informed decision. If you don't have access to the surface slab, ideally you want the radar system coupled with the surface that you're scanning. Some questions to ask your customer. What are you looking for and how deep is it? This will help you to determine which equipment set to use. How old is the concrete? This will help with dielectric, giving you more accurate depth readings. What type of concrete is it? Are there any metal shavings in the mix? What does the surface of the concrete look like? Is there any thick carpet or tile with a foam membrane? If you can poke your finger through it, there's probably too much of an air gap. Certain finished floors can also cause issues if they have a metal mesh. You might want to ask if you can move the holes, if it is recommended. Always ask how big of an area you need to cover. And lastly, is there anything else we should know about the job? GSSI is always looking for new ways to use GPR. Recently, we've worked with MIT to develop a system we call localized ground penetrating radar. Using an array of antennas, we're able to create a subsurface fingerprint of roadways. This fingerprint can then be used with other autonomous features in vehicles for localization. Thank you for watching this training webinar. If you have more questions, don't hesitate to reach out to the training department at the number below. We're here to help on your journey into the world of GPR. Check out the rest of the videos in this playlist for more information to get started with your new GPR system.